Oh, yeah, thank you. I just wanted to clarify this. This is not a tutorial. And you see, I'm really excited to tell you a little bit about my own research. So this is a project that has always been in my mind since I come to Oak Ridge as a postdoc, but I just got funding to do it 2 years ago. So I'm really happy to tell you about some new findings and basically to develop a new algorithm for accelerated Monte Carlo simulations, particularly for histogram type of Monte Carlo simulations. So this is a work that I do in collaboration with Marcus Heisenberg at Oak Ridge National Lab in the same group. And just 2 months ago, Alfred came up to Oak Ridge for the summer to help me out a little bit to work on the project as well. So yeah, I'm really happy to have more people to join the fun and join the mess maybe. So, so I will give you a little bit of the motivation why I started this project. It's basically all starts from that we want to do first principles based Monte Carlo simulations. And so you heard about rapid exchange Wang Landau just yesterday, and that was a little bit motivated by that because if we want to combine Monte Carlo simulations with first principles calculations for the energy, it's too slow to have a serial Monte Carlo driver. So that was why we started thinking about the parallel scheme for the Wang Landau sampling method. And then I will tell you why I went ahead to still thought about another algorithm to do even faster simulation later on. And then, so yeah, I talked about the parallel computing technique, and another route we took was the so-called histogram-free multi-canonical sampling, which will be the focus of the talk now. All right, so at Oak Ridge, we always want to have computer simulations to be able to compare with the experiments being done at Oak Ridge. And just if you don't know, we have Titan as a supercomputer at Oak Ridge, but at the same time, for the experimental side, we also have a very good neutron scattering, neutron source experiment facility. So a lot of the simulations and the experiments being done in Oak Ridge, we always have a drive to be able to compare with each other so that we can combine theoretical studies and experimental studies. So that was why the computational simulations at Oak Ridge are mainly focused on first principles calculations. And usually we want to study the real materials even. So a lot of the computing time or effort goes to this level, the ab initio level or the first principle methods. For example, density functional theory, and very recently quantum Monte Carlo simulations as well. But if you look at the length scale, what these methods can study, the ab initio or first principle studies can only deal with very small systems. Maybe they can go up to nanometer scale or a little bit bigger now. And then, but then if you want to study much bigger systems in a larger length scales, you have to go to molecular dynamics or Monte Carlo simulations, or well, in a bulk, and you basically mix everything and do whatever you want to do to a lot of approximations and models to study something even bigger. So what we were thinking about is, we want to bridge these length scales and time scales. For example, if you look at the left-hand side here, this is the these are the very accurate computational method for small systems, but they are very accurate because they take care of the quantum mechanics, electrons, and all these interactions into account. But the problem is that they're very powerful, but the problem is that they are only for 0 temperatures. A few of them can take care of finite temperature, but these are much more expensive. So on the right-hand side, we have the larger length scales, and usually we use Monte Carlo or molecular dynamics. And the good thing about that is that because now we have reduced models. For example, in Monte Carlo simulations, we have the Hamiltonian, a model Hamiltonian. And for example, molecular dynamics, usually you fit the empirical potentials and then you do the molecular dynamics. So in between is the density functional theory, where it is also actually, I would call it a model, because the model is hidden in the energy functionals. That is one of the assumptions in density functional theory. So our initial thought was that, okay, how do we build a bridge between the left-hand side and the right-hand side? And some people are already doing this, but for example, for molecular dynamics, there is the initial molecular dynamics that actually don't use the empirical potential. Okay, yeah, they don't use the initial. They don't use the empirical potentials, but they use the density functional theory calculations to directly inform the forces on the atoms, and then they do the molecular dynamics from there. So what we are thinking is that, well, we are not interested in dynamics. We are interested in looking at the phases and constructing the phase diagrams for real materials. Then a natural thought is that we want to do ab initio Monte Carlo simulations. So the thought then is that we want to do this do the same for Monte Carlo simulations. So this is where I started, and yesterday you heard about a package that I developed to incorporate Monte Carlo simulations with some external packages, especially for this reason, because I have helped writing a density functional theory code, but it's a big effort. So if you want to swap to another method, you don't want to repeat what is already available in the market. And that was why I developed a package like that. But at the heart of this package is still the basic statistical mechanics theory inside. So if you look at canonical ensemble, we want to be able to simulate the partition function or the distributions here. And for example, for metropolis sampling, you can simulate the canonical distribution. Or in one-liner sampling, you focus on getting the density of states. And with that, then you can study a lot of thermodynamics observables like the average energies, specific heat, and free energy or magnetization, all the things you can measure. And then you can construct a phase diagram. So we are actually following the same route. It's only that we want to do the energy calculations, which is much more expensive. So just a review of what is available, for example, is we have the metropolis sampling to look at the canonical distribution. Or we can also have one-liner sampling to study the density, the density of states. And I will not repeat that because probably you have already heard about this many times. So if we want to parallelize one-liner sampling, yesterday you heard about the rapid exchange one-liner sampling method. So given the background, so perhaps you already see the problems that for real materials problems, usually you have a continuous energy space. You have the you have a phase space which is not discrete. And so if you do the simulation especially for one lambda sampling, you have to define an energy range and then chop that into pieces, store it into array, and that introduced the discretization of the energy space. So this is one problem that we cannot get away with for a long time. This discretization problem, and it introduces systematic error, of course. So then we are thinking about, well, but we are dealing with continuous energy continuous variables like the energy. So is there a way that we can get away from this systematic error? Is there a way that we don't have to deal with it? So this is one motivation behind. And then the other motivation is that, so we are doing Monte Carlo simulations, but the energy is so expensive that we cannot really afford to do a normal Monte Carlo simulations. So here is an example. So when I was a postdoc at Oak Ridge, I helped develop a density functional theory code called the LSMS. A little bit background, this is a multiple scattering density functional theory method to calculate the energy. But at the end, it's a density functional theory method. So I try to incorporate, well, so this is done already before I went to Oak Ridge. So they have combined LSMS with one lambda sampling, and it was successful that they actually reconstructed the phase space, the phase transition for iron, and they calculated the Curie temperature very accurately, and comparing to experiments, very accurate. So the Curie temperature is a temperature where iron loses the magnetization. So yeah, so it was very computationally expensive that it even got the Golden Bell Prize nearly 10 years ago. And then when I came to Oak Ridge, I also helped a little bit with the parallelization technique, and then and that was why we come up with this rapid exchange method. And then, but if you think about that, we have already exploited all the ways we can use, all the parallelization techniques we can use to squeeze the last drop of flops out of Titan. So, for example, we have already used multiple Monte Carlo walkers for parallelization among the walkers. And then inside, yes. Right now it's for internal use, but there is also a plan to make it open source in the coming year. We are working on that. We are now working on the license problem. Yeah, so we have already used multiple random walkers, and then inside the DFT part, so inside one walker, and when we calculate the energy of the of a system, we have already used domain decomposition to further parallelize and speed up the code, and even better, we make use of GPU because there is a very intense linear algebra calculations inside the density functional theory. So we have already used all levels of parallelization to make our code run faster, but the result is that it's still too expensive. So if we use the entire Titan, keep running it, every second, it only gives us 1.5 energy measurement. So let's say if we want to do a Monte Carlo simulation to construct a one-dimensional phase space, for example, the phase space in the energy, so basically one lambda sampling, you need at least 10 to the power 6 or actually 10 to the power 8 to be more accurate Monte Carlo steps. So if you do a back of the envelope calculation that takes 1 week for Titan to run non-stop the entire machine, 1 week to finish only one Wang-Lander sampling. And this is not a computational cost that we can afford. Even I just sit on top of a computer. So that's why then we are thinking we need to go back to the basic and ask, is there a way, or we have to think about a better way to reduce the Monte Carlo steps needed. And so this is how these histogram-free accelerated Monte Carlo scheme came up. So now I just outline the algorithm first, and then I will go into details how every step works. I hope at the end of this week you will not be bored of seeing all these green boxes, because all these green boxes I use are for algorithms. It's very similar to Wang-Lander sampling. We also start with the a guess of the tensor state, and here we also have a correction factor, but this time it's not just a number. This correction is also an expansion. So we assume that we can write the tensor state in basically a series, a linear combination of basis sets, and then we write the correction in the same way. So in the simulation, basically we do the simulations to estimate the tensor state just like in Wang-Lander sampling, but then in this problem, it reduces to fitting the coefficients G and C in the algorithm. So we start from an initial guess, just like in Wang-Lander sampling. We set the initial guess of the tensor state to be 1. That means no energy degeneracy. And then we generate a data set containing k energies. So when we generate this data set, this is actually a Markov chain, and we accept or reject with the probability very similar to the way that Wang-Lander sampling does. It is inversely proportional to the instantaneous density of state, but the difference is that this time we don't change or update the tensor of state at every step. We only update this at the end of an iteration, just like what you are doing in multi-canonical sampling, if you're familiar with that. And then, so at intervals, we use the data set to find the correction. That means we use this data set to fit these coefficients C in the correction. And then after you have the correction factor, then of course you can update the tensor of states. And then you iterate this procedure until this correction becomes 0. Yes? Between what? Yeah. Yes. Here? Yes. It's the same thing, but I don't do this at every step. Now I do this after I have generated the entire data set of energy. So I have already generated a Markov chain of energies, and I use the entire Markov chain to update the tensor of states. This is the difference. But in essence, it looks very similar to Wang-Lander sampling, but this is the difference, actually a very major difference, because here then I update the tensor of state with a set of energies, not just one. And this actually preserves the detail balance that I discussed with Michael. But yep, so this is so you can see this scheme is very similar to Wang-Lander sampling, only that right now I don't have an array of dense of state anymore, but instead I have the analytical expression for the dense of state and the correction. Yes. I have an yes, I have an expansion. Right. Right. Yes, and so here I don't fix the number of terms. N is also found on the fly during the simulation. So I will describe how to do this. Yeah, but yeah, the basis set is, so I have not said what basis set I'm using here. And actually this is, I would say, is still a research topic. Which basis set would be the best for general use? I would think actually it should be different for different system in general. So I would say this is, here there are a lot of things that you can play with and a lot of things that people can improve. And I don't claim that I know everything, really. So if you are interested, then I would be really happy that anyone can come up with some ideas to improve the scheme. And yeah, we have a lot of things to try out here. Ah, okay, here. So it's a Markov chain. So when you generate this data set, you start with an initial energy. And then you, yeah, step by step. And then you generate the next one. Well, this is something that you just fix. So for example, I can say I want to have 1,000 data points in this data set. Then you just generate 1,000 energies. Yeah, sure. But you can also change the size of the data set. So this is something that you have to fix at the beginning of the simulation. Yeah. Every time. Yeah. Yeah. Okay. Well, actually, the third thing is very hidden. And I discussed this with Martin Weigel last month, and this was a confusion. So here I, instead of, yeah. Yeah, yeah. So we don't have the histogram anymore, you see? Yeah, yeah. No. This is something that you just say, like how many Monte Carlo steps you want to do in a metropolis sampling. Yeah, it's just a number you fix. You can choose it. Yes. How can I calculate C? Yes, so this is the next slide. Okay, so any more questions before we go on? Because otherwise, everything I said from now on will be blah, blah, blah if you don't understand. Okay. All right, so how to fit the coefficients is the core of the algorithm. But I have to start from basic statistics first so that you will understand better. So first, you realize that I don't have a histogram anymore in the algorithm. So why is it? Because now I store everything in the data set like this. And if you think about that, I can use this data set to construct the cumulative distribution function or cumulative distribution histogram. And well, if you step back a little bit, this is related to the histogram. It's just, you just sum up the histogram up to a certain point, and then you have this cumulative distribution function. So with these, then one very important concept in flat histogram methods is that, well, we want to have flat histogram because we want to visit the energy space equally every time. We want to generate states that are roughly, well, you generate roughly the same number of states in your energy space. So if you translate that concept in the CDF into the cumulative distribution function, that corresponds to a straight line with a slope 1. So let's say if I have a CDF, the cumulative distribution function like this, you know if you have a histogram, it should give you something like this. So then you can ask the question, how much your distribution deviates from a flat histogram, right? So if you do this, then it's basically you're asking a question, well, or you can flip it another way around. You can decompose the cumulative distribution function into a straight line plus a remainder, which is the difference between these curved straight line. Right? So if you do this, then you plot this out, then you plot the remainder out. So it's something like this. So why do I need to do this? Because if I know how much it deviates from a flat histogram, then I can use this to update my sampling weight. So then next time I know that this part I should not sample that. Oh wait, this part I should not sample that much, and this part I should sample more. So, and oh wait, sorry. Okay, so here is how to combine this concept, combine the remainder, and try to find out the coefficients from the remainder. So if you go back and look at the definition of the cumulative distribution function, this is the equation you just saw. This is the definition from the histogram. So you basically sum up, you add up the histogram up to a certain point, and it gives you this CDF. But just the last slide, I also make an assumption that the CDF can be decomposed into a straight line and the difference. So I'm just rewriting this equation like this. But if you combine these two equations, you know this part should be equal to this part. And then, let's see, you make a differentiation. So you differentiate the density, the cumulative density function with respect to energy, like this. Then, you know, the left-hand side will give you the histogram. And then the right-hand side will become like this. So then you know, okay, then this histogram can be, if we think in terms of histogram still, but bear in mind that I don't have histogram anymore. If I look at the histogram, then it's a constant plus the deviation from the ideal sampling. So I know, this must be related to my correction. So I just take this as a correction, add this back to the density, the guess of the density of state, and then I go to the next iteration. So this is actually a little bit different from the multi-canonical sampling, still a little bit, because in the multi-canonical sampling, you work directly with the histogram. And here, we update the density of state with the exponential of this, with the exponential of the difference from the ideal sampling. So basically, we give the spaces more weight to sample in the next iteration if you don't generate this well enough. So there is an exponential factor there if you compare with Muka. All right. So so we know that this remainder is related somehow to the correction, but we have already made an assumption that the correction can be expressed in terms of the linear combination of the basis set. But you know here I have a derivative here. So I can also do the same for the remainder, but this time I know the basis set that I choose for the remainder should be the derivatives of the original basis set that I use to expand the dense of state and the correction. All right, so this is what I'm doing here. We expand the remainder also as a function of the basis set, but this time this basis set is not the same as the one I use for the dense of state and the correction. It is related to that by a derivative. And then if we can do this, then we know the coefficients for this series can be found from a Fourier transform or an orthonormal condition with this formula. And that's why when we choose the basis set, we have to choose the orthonormal one. And this is the trick. And there are some, well, if you choose a basis set that is not orthonormal, then you have to do some other optimization procedures to find the coefficients R. And it's not as convenient as doing a Fourier transform, but it's still doable. So in principle, it's still doable. Oh, no. Keep it simple, yes. Okay, so if we know the coefficients, and then now we can find an expression for the remainder, then the remaining problem is to find out how many terms we need in the expansion. Is still unknown. So the procedure we use is as follows. Every time we put one term in the sum, we put one term in the expression, and then we perform a statistical test to see, to calculate the probability that this expression fits our data. So in other words, we perform a statistical test to see how well this function fits our data. So if it's not good, then we add one more term, do the statistical test again, and see if it's good or not. And we repeat until this statistical test gives you a good enough number. So usually this kind of statistical tests are between 0 and 1. So then we say, well, if it gets to a half, then it's good enough. But this is also adjustable. No. I'm not talking about those tests. I'm talking about those statistical tests where you really measure how well your distribution or how much it comes from. Yes, this is the next thing we use. We use Kolmogorov-Smirnov, but you can also swap. This is not a fixed thing. This is something that you can still look into, which statistical test you use. Yeah. No, this is not the same. This is not the same as those. Yeah. 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 Okay. Yeah, it will be. It could be corrected later on. it could be corrected later on. Okay, so this is the entire algorithm. So now I want to see how well it works. And I apply this to a toy game, toy model actually. 10 years ago, I was sitting in, I was a summer student in David's group, and then I was sitting in the office. I learned about one-letter sampling already, and I was thinking, how can I apply this to something else that is related to my master project research? And at that time, I was doing a lot of numerical integration. So in one afternoon, I was daydreaming, and I thought about, this could be doable. So, but I don't claim that this scheme, so I apply one-letter sampling to do numerical integration, but I don't claim that this scheme is a good scheme for numerical integration. But very recently, just last month, there is a group taking this prototype model and improve it. So, and they prove that, so with the improvement now, it's good for numerical integration. So if you really want to use one-letter sampling or flat histogram methods to do numerical integration, pay attention to a paper that will be published very soon in computer physics communications. So the idea is as follows. If I want to do the integration here, I want to integrate the function y of x. So if you do the trapezoidal rule or rectangular rule, you sum up all these rectangles together, and it's basically the area on the curve. So if I flip that around, I asked how much of this region corresponds to a certain value of y, and I can draw a picture like this. So I can draw, well, okay, so if you are asking this value of y, so these are these gray regions that gives you, that corresponds to this value. So if you flip that around, then it is like the gray area is the red area times the height, which is y, of the rectangle. So then the gray area adds together will be the density of state of the red area times y. So then I can flip the problem around and say, okay, so I just sum up all these gray areas. If I know the density of states of this gray area. So it's just a way to play with one-letter sampling and see how well it does. But then the good thing about this is that this is actually a model with continuous phase space, and it has an exact answer to compare with. So that's why I take this as an example to test whether my scheme works well and how it compares to one-letter sampling. Turns out it's actually more challenging to do than most physical models. All right, so this is the results. I take 1,000 data points in my data set, and then I take the sine and cosine series. The sine to fit the remainder, and then the derivative of this, so cosine for fitting the density of state and the corrections. And then we use Kolmogorov's Minov test to see whether our analytical expression is good enough for the data. And this is a graph plotting the value of the estimation of the integral versus number of iterations. And you can see, actually, when I see this graph, I don't believe it, because basically it's just fluctuations around the exact values starting from the beginning, nearly. And so, and then I look at the another example where I have this time 2,000 data points in my data set. Then I see a problem. And you see everything has been underestimated. So then I was thinking, hey, it should not be, because you expect that if you have more data points, you should improve your answer. So, so the reason why is that in this scheme, if you have more data points, actually you have a larger risk of overfitting the analytical expression. So we need a way to improve that. And all right. So I will talk about the improvement later on after this slide, but just to let you see how the density of states is like comparing to one-lambda sampling. Even for, well, so this is the 1,000 data points case. The case you see, the first example you see, which is very nicely estimated. So you see the black curve here, which is obtained by this algorithm, is much smoother than one-lambda sampling. And this is exactly because we don't have the bins anymore. So with the bins, you still, this is still considered to be, well, so basically when you have the flat histogram, you do all these estimation and then you update it density of state, but you still have these fluctuations among the bins. But with our scheme, these fluctuations is gone. But then what we get is a little bit of these slower oscillations. It is because of the sine and cosine basis set. And that's why choosing a correct basis set is still a research problem, and we probably need more help here from the from people who are more familiar with the math. But one thing to pay attention is the number of Monte Carlo steps needed. In our scheme, we only need around 10 to the power 5 Monte Carlo steps, where for one-lambda sampling to converge, it takes 10 times more of Monte Carlo steps. Yeah. Yeah, so this is just an estimation at this point, and we exactly asked this question, but how do I tell it's converged? So right now I cannot. Right now I just look at the graph and say, well, so I take, for example, 100 iterations to be the estimation. But then here is really just an estimation. It's not a quantitative measurement. But later on, we introduce a quantitative measurement to really tell whether it has converged or not. So yeah, so you see the problems already here. All right, yeah, so this is the observation actually we see from this scheme. And yeah, so and there are also problems that you just pointed out, and I will answer. I will give a good answer to this after this. So basically, the speed up comes from two factors. One is the so this time we actually move the random walkers intentionally to get a flat histogram. So we move the random walkers intentionally such that next iteration it will better approach flat histogram, and it's not like one-lambda or multi-canonical sampling. You generate a histogram and then just use the histogram, or you update the density state one by one, and this is not systematic and it's not intentional at all actually. But in my scheme, I intentionally make the correction in such a way that I compare this with a straight line, and this is actually intentionally to push the random walker of the next round to sample better the flat histogram. It does that, but it also multiplies this with the multiplication factor f, right? You remember? And this is actually also a magnifying effect here in one-lambda sampling. But this time, I have the exponential instead of a fixed factor. Right. Mm. But then that is multi-canonical sampling, basically. Right. Yes. This is something we need to do, actually. Yeah, we need to separate these three things to do, and that's why I need some help. I don't have the time to do all these experiments. All right, so maybe I will skip this one. Yeah, so going to the convergence problem. We want to be able to control the convergence, and one thing we came up with is that, well, you know that the correlation factor is an exponential of the difference between the sample and the ideal sampling. So then if I use a milder correction factor, then I should be able to see the convergence better. So basically, I'm slowing down the updates right now. And then you see that, okay, so this, the density of state still looks okay, but it's not as good as before. And for the 2,000 data points case, you see that it sort of converged to the exact values. You see that now it really shows a convergence behavior. But the problem is that you still don't know whether I cut off here or I cut off there. And you only need to, well, the only thing you can do is to run it long enough, and then you say, okay, so probably this point is good enough. But then this is not satisfactory still. So what I really want is to be able to control the convergence quantitatively. So the design features we were thinking about is that, well, we want to have a quantitative measure to see whether the estimated analytical form is a good fit to the data. So before we use Kolmogorov-Smirnov, but then later on we define another quantity for doing this. But we keep, actually let me show this. So for the first part, we don't use the Kolmogorov-Smirnov test anymore, but instead we define a new distance measure that measures how much you deviate, how much our analytical form deviates from the cumulative distribution function. And we measure that, and then we actually use this as a criteria to cut off how many terms we need in our expansion. And then for the second criterion, the second feature we want to have a quantitative measure to tell you should stop the simulation now. And so here we keep the Kolmogorov test for terminating the simulation. And then for the third feature we want is that, well, if you increase the number of data in your data set, you should not get overfitting. You should be able to improve the answer. So if we do the two things here, then this actually automatically follows. Yeah, but it's much more sensitive. It's much more sensitive and it's much more sensitive, and that's actually why we get overfitting before. So because it's too sensitive, and you need a lot of terms to make the Kolmogorov test happy, and say, okay, now I'm satisfied. It's a good statistics, but then you use too many terms in your expansion, and that leads to overfitting actually. And that's why this distance measure is actually not as stringent as Kolmogorov-Smirnov. Distribution? The CDF, the CDF every time you generate from the data, and the analytic. No, here in the distance measure, we don't need to define that. Before it Kolmogorov Smirnov, we just take the one in the standard. I forgot the form. Yeah. Yeah, it's actually a distribution function underneath. Yeah. Yeah, but then it. Yeah. Yeah. Okay. Yeah, we can discuss after the talk, because I'm already running out of time. But yeah, we can discuss this later. Okay, so lastly, I want to show you the results we just got. So with this improved scheme, you see that you see a better convergence behavior, even if I just use 1,000 data points in the data set. But the estimation is not too good. It overestimates the integral. And then let's say, but here we have a very clear indication of how we cut off the simulation. For example, here, the Kolmogorov test passed the 0.5 mark at only the 12th iteration. So we can say, well, okay, we stop here and ask what answer we get. So this is the way we now control the convergence and tell when to stop. And then if we increase the number of data points by 10 times, and then you see the estimation gets better, and then it actually really comes to much closer to the exact value. And then if you increase that further, okay, then you see right here, you need a little bit more iterations, because now you have a lot of data points, but you see the behavior is much more controlled, the error bars are much smaller, and the estimation is much more accurate. And yeah, so this is basically, it satisfies all our 3 wishes in our wish list. So right now we are quite happy with this. So I hope I have presented the new algorithms to you, and I would really love to continue the discussion. Yep, thank you. Wait, I forgot this. Very important. Advertisement. So next year in the APS March meeting, the American Physical Society March meeting, I think most of you know about this. It's like nearly the largest event in the US for physicists. So we are organizing, David and I and Marcus Eisenbach at Oak Ridge, we are organizing a focus session for advances in computational statistical mechanics and their applications. And the reason for us to organize this is actually last year we went to the March meeting, and then we saw that the March meeting was now quite dominated by focus sessions. And we cannot find a session that we can really submit our abstract to. So then we were thinking, let's make one, and so that all of us can have a place to get together and submit our abstract to and get more fruitful discussions. So this is the reason behind that. And so the abstract submission will be, I think it's not open yet, but it will be due somewhere in mid-November. And then I think now they are accepting nominations for invited speakers. So if you want to invite yourself, or if you are sending students to the next year's March meeting, please consider submitting abstracts to this focus session. Thank you very much.